Good afternoon. It's good to see you again. So welcome to the fourth and last session of our workshop that is organized by the 3D geomodeling team of the Geological Service for Europe, the GSEU European project. If you join us for the first time, this workshop is related to the uncertainties within 3D geomodeling. And we already had a presentation and interesting discussions about the concept and sources of uncertainties, about methods and tools to calculate them. And this morning we had some presentation, especially from geological surveys, European geological surveys, about case studies related to 3D geomodeling and uncertainties. And the session is going to be recorded as the others, and you will find the replay afterwards on the GSEU YouTube channel. The link to the detailed program is now on the chat, including this afternoon and the whole workshop. Still the same message for the presenters. If you wish, you can send your presentation to Daniel, Marco, and me for sharing in case it is needed. And so after the operational way of working of the geological survey this morning, let's talk about communication of uncertainties in various applications. We are going to have information and sharing of experience this afternoon. And also don't miss the interlude, our interlude with Daniel and the Menti game in about 40 minutes. But before that, we have two presentations, and I propose to you to start right now, so we will have a bit more time for the rest then. The first presentation is from Santiago Martín Alfageme, from the Spanish Geological Survey, and I hope you're there, Santiago. Yeah, okay. You can start sharing your presentation if you want. I like very much your title, Santiago. So I don't know if you will conclude that there is two kinds of people in the at the end of your presentation, but you are going to share with us a recent experience that occurred in the course of the GSEU project. So Santiago, please.
Okay. Hello, everyone. And I am going to present a topic related with blank spaces and maps and fake news. The reason of choosing this title of the famous spaghetti western is that several actors with conflicting interests were involved in this matter. And in addition, it took place during the hot Spanish summer of 2025, just like in the film, and it was all happened in the far west. Well, just a little context. In last summer, Spain suffered one of the worst periods of forest fires in living memory. And because the reason behind were high temperatures, strong winds, and you can see, for instance, the satellite image that show how smokes from the fires covers many areas of the Iberian Peninsula. For instance, in Madrid, you smell the smoke like in many areas. Well, let's go to the good part. Maps from CRM, the famous map from GSU project, and maps from Spanish fires. You can see here forest fires over a long period of time. The red dots correspond to indebted fires, which are the majority, unfortunately, in Spain. This includes agricultural activities such as stubble burning, which lead to fires. This is the most frequent reason for forest fires. In the northwest, in Galicia, is the most dense area, and this is due to diverse factors such as the distribution of land in that region, the density of the projects, and other reasons. But you can see that fires are in this period all over the country. Another map. This is in a more recent period, also covers whole of Spain. This is burned areas, and again in Galicia is the most frequent part. This is the Spanish forestry map. By the way, it's no surprise, it's quite similar to the geologic map. And these areas in green correspond to mountainous areas. The dark green corresponds to conifers, light green to deciduous trees, and orange to mixed areas. The blank areas usually are tertiary basins, and usually there are no forests there, but crops. Okay, this is a well-known map. This is a screenshot from yesterday from our famous AGD8 database. And once again, there is a general distribution of the occurrence of critical raw materials. You can see a lot in the west of the Iberian Peninsula, but as well in many mountainous areas. And to support the previous map, this is a map published by us. This is 2 millions. Yellow colors corresponds to tertiary basins, and the other is Paleozoic and Mesozoic. So most occurrence occur in hard rocks. And let's go to the bad, to the misunderstandings and the uncertainties. In this way, in that sense, I am going to show you some maps that provoke or were the basis to the fake news. The first one is a well-known map, printed map, the CRM hard rock deposits of Europe of 2024, edited by Euriosurveys and BRGM. And if we focus, make a zoom on the Iberian Peninsula, you can see the data available at that time. It all concentrated on the western part of the peninsula, and it was the data available on that time. And a blank is on the eastern part, but as you know, no points doesn't mean no data. This map was published, and immediately some Spanish economic newspaper, Salmon Press, published articles such as Expansión. The curious thing is that the press article described a mineral exploration plan carried out by the ministry, and only used the illustration. This is it's a draft of about the map, the previous map, as a reference, and this contains an error. It was not a rare element that were shown in the map. We can compare two maps, and this is what I said previously. There are a lot of more occurrence, that are not uploaded in EGDI. Let's go with the fires maps in August. This is a map published by a serious newspaper, ABC, and during those days, and it comes from, as I said, a national newspaper. All fires were concentrated in the western part of Spain. And again, with the same as the CRM map, you can see that no surprise, the fires were on the most frequently areas, but surprisingly, there were no fires on the Mediterranean area, only in the west. Okay. And let's go with the ugly fake news. I put it here a sentence of Renata Barros. She is the leader of Work Package 8 in the GSEU project, and the detail that an article that she published about this issue. Maps don't lie, but humans do. At the end of the August, in TikTok and Facebook, someone published in the social media superimposed two maps, one published by the financial media that I previously showed, and another showing the fires. And the conspiracy theory is served. Everything is better understood together. Do you think that it's strange? And even they elaborated some arguments. The first is just a crude geological explanation that fired areas are better to drill, and you can see the geology much better. And also the second one is that it's a fake that it is for a long time in Spain that burned areas can be changed easily to urban areas, or in that case to a mine. That is not true. There is a forest legislation that after a burn you cannot change the land use for 30 years. The third one is just an explanation of the importance of the rare earths, and they are really, really expensive. And the last typical conspirational phrase is that ask yourself, why don't media outlet explain this is a plausibly theory? By the way, the publication contains some hashtags referring extreme right political party. Okay, the fake news got a lot of likes, and after a few days there were some YouTubers or channels that talk about the new, and they give credibility to that. The first one is a news channel. The second one is a YouTuber, and of course they level up the ideas. They accused the Spanish government with the European Commission are planning to convert that areas in lithium mines, because they related that information with a visit that made the Spanish Prime Minister to China in May in that year, and where he met the industrial sector with lithium as the main topic. So this was really a mess to us, and it was really very quick spreading over internet. And then the final duel of how to deal with the social media. I think the typical survey, geological survey reaction is a serious press note, but it's a poor impact on it. We were lucky because some anti-fake journalists contacted area surveys, and they gave some explanation, and they delivered to area survey said you can call the Spanish Geological Survey and get more information. And in the same way as the fake news, this journalist gave some information. First is a warning about the map that links fires and critical raw materials. Second one is that the map, the CRM map contains 31 sites, but 17 are already operational mines. That the urban planning in Galicia not allow in Galicia, Castilla y León, and Extremadura the areas with more fires doesn't permit any change of land use, and the content doesn't provide any evidence of these fires will facilitate the extraction of minerals. That was our part, and the fires are in the more traditional areas where historically where areas were burned areas, and the motto is correlation doesn't imply causation. More in deep, we were consulted, and we explained rare earth. We say that map doesn't contain any rare earth elements, and on the other hand, that anti-fake web consulted these 70 exploitations, and according to public information, these companies, no one were from the Chinese. So each argument from the fake news one by one was dismantled, but this anti-fake argument, this anti-fake web page, the web page, the name is maldita.es, and I think in every country would be can be fakes that locate news against fake news. And the effect, in the similar way as like the fake news, was that this content was spread among serious media, and others replicates, including the Spanish largest agency, EFE, which have produced its own article and ask again the Geological Survey for information. So I think it's a good strategy to contact anti-fake news journalists. And this is a happy end. And thank you for your attention.
Thank you, Santiago. It's a very interesting experience. Of course, it's not directly related to 3D geomodeling and uncertainties, but to uncertainties anyway, or to information. And I think it's a good example to say that, of course, what we produce in terms of 3D models and eventually uncertainties associated to them has consequences, and sometimes the consequences are not the one we want. do you have some comments or question or on this, of course, true story presented by Santiago?
Mm-hmm.
Yeah, we have Mitro. One question, Mitro. Yeah, please.
Yeah, I have a comment. I've seen this map on the internet, and there is noted Polechivsky deposit, lithium deposit, as working one. But at the moment, they only have proven reserves. They are planning mine. It's not working. This is not true. This is not true. In Ukraine, there is no mines that are mining lithium ores. No petalite or spodumene.
Mm-hmm.
So this is my comment. And also, often there are misleading rare earths, rare and trace elements.
Yeah.
Maybe this is the reason. So rare earths, it's lanthanoids, okay? Yeah, but rare is other group. Trace is other group.
Mm-hmm.
So this could be a...
Yeah,
okay, thank you, Dmitry.
Yeah, thank you.
Yeah. Thank you. No, we know that because we provide information, Dmitry. But we also
know that, but journalists sometimes do not understand the difference.
No. We have we also explain that this is occurrence. We also explain that only one every 100 occurrence as average becomes a mine. So this is another important point. And but the most important thing is that I think in this issue is that there were no available data at that time, and we know right now we have a lot of more data on the map.
Oh, I've seen a lot of publication on Spanish pegmatites, spodumene, petalite, rare metal pegmatites, so LCT type. And of course they are present, but not a fact that it is viable to mine there. That is the question.
Thank you. I think that at a certain point the arguments are not no more efficient. I mean, but you know that even better, Santiago, because you really liked this kind of thing, and maybe it was a good way to ask some help from specialists than to give a kind of a formal response that, as you said, has probably no effect. Yeah. Is there any other question or comments for Santiago? I see there are a couple of them in the chat. There are mainly comments. You will read it, Santiago.
Okay.
And thank you for sharing this experience. So it's time to, and maybe we will come back to that during the discussion, of course, at the end of this session.
Okay.
Thank you, Santiago. Thank you again for that. Let's move now to the next presentation by Mats Svensson from the Tyréns company. And Mats is going to talk us about the uncertainty in 3D geomodeling and the relation with the infrastructure projects. Please, Mats. We can see your first slide. It's okay.
Thank you very much. I hope you can hear me as well.
Yep.
Yeah, as was mentioned here, I work for a Swedish consultant company in the industry of the built environment, and I will talk about handling of uncertainties in geological and geotechnical layer modeling in infrastructure projects. That is not so often doesn't show up in social media, I must say. What we have done is we have developed a platform, a digital platform for all geotechnical related information that can maintain all the data we collect from archives and fields and labs, and also the models that we analyze and like a bedrock surface and so on. And we also have delivery specifications for standardized handling of geotechnical structures like piles and so on. And right, this has been developed over the more than 10 years, as you can see, and in a number of different R&D projects, I would say. And the one I will talk about is let me change to the laser pointer. This R&D project called Bedrock Models, and where we also developed uncertainty models. So this is just a teaser of what you're gonna see here. This will end up in 3 models and an uncertainty map. I will come back to that one in a few slides. So first of all, why uncertainty models? In our industry, geotechnical models are always a discussion, and differing geological and geotechnical conditions is often a reason for claims after the project or during the project. And if we have control of the uncertainties of different geological features, it's possible to optimize planning of the investigation program and other things at all times during a long project. And it also, maybe most important, gives a clearer risk sharing in contracts and hence less claims. And of course, it's also sustainability feature here by optimized mass handling, which is a big driver of the climate change, I would say. So the process we are working on is, first of all, we also look at if we have any maps before we go out in the field to do the investigations. We do the fielding investigation, and that goes into this database, our common data environment. We call the concept we have, the database, the GeoBIM concept. We do the interpretation, we do the modeling, and then we have added this part, we have added this to the process. We nowadays do uncertainty modeling, which we couldn't do before. So we include the knowledge of the uncertainties in the geomodeling. And we could loop this one until we are happy with so that we get the low enough uncertainties. And once we're done, we can use that, decide, like locking that geomodel and use, including the uncertainties, for all the further design work. So how are the uncertainties calculated? We use 2 types of in-data. The individual uncertainties of each borehole, you could say, each investigation could also be geophysics. That's one part. We also use traditionally the distance to the nearest investigation. And those 2 are the in-data to ordinary kriging and Monte Carlo simulations. In the R&D project, we used 1,000 models for the Monte Carlo simulation, but in the real, on a daily basis work, we normally satisfied with about 100 or 200 iterations. And that gives this is like it's an Excel sheet more or less, where every row here is a boring. We have the sounding here. We do the interpretation, which is our best guess, and which is the shallowest reasonable depth for this specific borehole, and which is the lowest reasonable. Most often we do use a 95% probability. And the result that comes out is this. We get, on the left figure, 3 different models. The best guess is the most probable one, the green one in the middle, down here. And the upper and lower ones are the shallowest reasonable model and the deepest reasonable model. And you can see some red areas here. Those are, in this specific case, the uncovered bedrock and survey the true surface that we could calibrate our model to, which I will show you in a few minutes. What we also do is we could visualize the uncertainties in what we call an uncertainty map, where the red areas illustrates areas where we have high uncertainties and the green areas where we have low uncertainties. Because this is the reality. It's not we're not always in a sedimentary environment, and even then it's not completely flat surfaces. So we have, on a short distance, we could have quite some changes in the top of the bedrock, as an example. So this is what we, at least in Scandinavia, are facing. So in this R&D project, we wanted to know how good is the model. The red one here is our model, and in the green one is the surveyed uncovered area. So we have a volume of misfit volume where it is more rock than expected, and we have another volume where we have more soil than expected. So what we did, we were lucky to get 5 different areas where we have uncovered bedrock surfaces. We call it the truth, and they were very carefully surveyed. And what we did, we looked at the misfit between the model and the true bedrock in those 5 different cases. Sometimes we got more soil, in some areas we got more rock, and overall, you can see we had the biggest misfit was 0.9 meters, and the biggest misfit in the smallest biggest misfit, so to say, was 0.4 meters, and those were in the real vicinity of the areas where we have very little information. So in case 1, the one you've seen now for the 3rd time, you can see we have in the blue areas, the dark and yellow, light blue areas, we have a misfit of less, around 10 centimeters, and the biggest misfit seems to be quite high. I would say that the average depth of this bedrock is about 10 meters below the ground surface. The biggest misfit we have is above 1 meter, but that is in the very corners of the area where we have more or less no information. In case 2, the same pattern here. You can see there are some red, the true surface standing out above or below the upper and lower ones. But what is interesting here, we have some real big dips in a few points here. You can see them on the uncertainty map here as well. Those red dots in the blue areas with very low uncertainties. And why is that? Well, it was shown that in these points, the sounding wasn't done according to the standard. The standard says in Sweden that if you think you have hit the rock, you're supposed to carry on until you're at least 3 meters in what is interpreted as a bedrock, which they haven't done here. And that's why we had to add quite a very large uncertainty in those single points. It may have been a boulder or something. That is how the standard is used. So it's also a way to detect where you haven't followed the standard. It turned out. So also some other interesting results that this is one, many boreholes is not always a guarantee for a precise model. You can see in this circle here, we have a rather high number of soundings, but still we have a red area, which means even if we have a large number of boreholes, we still have high uncertainties. And the reason for that is that each sounding has large individual uncertainties, and that overrules the large number of boreholes. So this means we can use as a basis for decision of changing method. And in this case, instead of sounding method, we decided to do some core drilling here just to find out is it a very fractured rock, which was expected, or something else. So this is another way to make use of the uncertainties. We also did a test where we added geophysics. In this case, seismics. You can see on the left uncertainty map, we have quite big area where we have high uncertainties, yellow and red areas, whereas when we're adding the seismic data, where we also have an interpretation of the bedrock below every single microphone or geophone, we get much lower uncertainties overall over the whole area. So this is a clear indication of that geophysics is adding value to lowering the uncertainties. So the value of being certain on the uncertainties, so to say, is that you could optimize the investigation program. And that is almost most value for money. And we also, this is very important, you also get a confidence in the team during the whole project. You get a feeling of that you have control. You know what you're doing. You know you're doing the right things. And also, as I mentioned before, this gives you a much clearer risk sharing in contract between the client and the contractor. Otherwise, this is typical issue for claims. So this means less claims if you have a clear way of identifying the uncertainties. So why less claims? So what is the reason? How does it work if you look at the contracts? Well, those three lines here are, as you see, a 2D sketch of the most probable bedrock model, and the upper and lower reasonable bedrock models, as I've shown before. And of course, we're not perfect. This is the true bedrock while surveying it. But this means that in the areas where you have more bedrock than expected, there is no problem. The client could pay the contractor these extra money that it costs. And also in the areas where we have less bedrock, well, and this is the same case. You also have no problem of paying the contractor, but in this area where if you look at the most probable bedrock model, which is and don't take care of the uncertainties, which is the fact that the contractors most often behave. But if you have such an uncertainty model, it's no problem. It is very clear this was given in the contract, so you get no extra payments even if you have more rock than the most probable bedrock model. And if you want to get more details on this type of algorithm, this type of model, and look deeper into the different cases, there are 5 cases here, you can find it in this paper from the conference paper. You can download it from the ITA, International Tunneling Association bookshop. So we had a few funders of this project, and we say thank you to those, and thank you for your attention.
Thank you, Mats. Thank you for this presentation. Is there any question from Mats or comments? I see none in the chat. So still the same. Please raise your hand if you want to say something. Yes, Charlie.
There is a question in the chat you can go to first if you want.
No, go on, please.
All right. Okay. Sorry. Yeah. So thanks. I found that really interesting. I was just going to make a comment, I guess, about, I think you're saying you're using a 95% prediction interval, or was it 90%? But isn't it the case that you would expect then that the true surface would actually be outside 5% of the time? So, well, I wonder if that's a reason that you can even, you can say, well, we shouldn't have to pay extra because these lines just mean, the truth will be inside 95% of the time. If it's outside 5% of the time, then that's to be expected, I guess.
That's correct. It's exactly like that. So it's expected to have, if we use the 95%, it's expected to get 5% outside, the upper and lower limits, so to say, and that is what the client then is expecting to pay extra, but not more than that.
Yeah, cool. Okay.
Yeah.
And do you find that is the case, that you tend to get it right, that there is 5% outside the lines?
Well, we're quite confident. We since we have actually these 5 uncovered and surveyed clean bedrock areas, which we could actually have you couldn't get any better ground truth. So we're quite confident. And then when it comes to, when we now used it in, I would say maybe 50 different projects on a daily basis, you very seldom get the whole area uncovered. But it's definitely clear that we have much better prediction than we used to have before, and we see that the clients are happy with this. We haven't reached one of the biggest client to us is the Swedish Transport Administration. We haven't yet seen that they are asking for it in the tender documents, but they've actually, during the projects, for those their specialists who are aware of this methodology, they've actually started to ask for it. Right now, we got this request just the other week in quite a large railway project I'm working on. So it's and that's a milestone, because the Transport Administration they always the last in the queue to react on this type of new things that come up.
All
Yeah.
right. No,
Thank you.
Thanks. Really interesting.
Yeah, thank you. There is a short technical question in the chat from Ian about software. Which one are you using for modeling, and how do you transfer this geo model to the BIM?
So I don't understand which SW. What does it mean?
Software, I think. Which software are you using for modeling?
Oh yeah, sorry.
I try to rephrase.
The software. Well, the software we use is it's a Python script that is based on. I saw you had Florian Wellman in one of I think it was in the first session, and the GEMPI methodology, which is it's a largely modified version of their methodology. They're using kilometers in their depth scale. We're using meters. So, and we have of the infrastructure projects are most often very elongated, so it's a big difference there. We had to modify it quite a lot. So that is the software. So it's our own Python script, so to say. And how do we transfer it to the BIM? Everything has to end up in any of the Bentley software or Autodesk, like Civil 3D. So what we do is that within the GeoBIM concept, all the models we do and all other things, to get it into the BIM software, we have to produce, in this case, what we call the civil 3D surfaces. So that's the way to transfer it to the BIM world, so to say.
Yep. Thank you. So yeah, let's take time for a quick question or comment and a quick answer then. Chris, please.
Yeah.
Oh,
What happened?
sound issue.
Okay. Echoless this time?
Yeah,
Yeah.
okay.
Yeah.
Yeah.
Nice presentation. I think it's a good example of bridging the gap between geology and geotechnical engineering. And this was more in the light of volume calculations. Do you have any plans to further incorporate these types of layer models into the geotechnical engineering process? Are you working on that?
What we do as we have a short answer here. What do we have done? All the functionality. We have a number of different automatizations and very small ones and quite some big ones like this one in our concept, our platform. And we have actually implemented all this in the Teams, Microsoft Teams environment. Because that is where all our employees in our company, we're about 150 different geotechnical engineers. So we have implemented it in there, and so that's where our geotechnical and rock engineers working with this on a single on an everyday basis. Well, we not have any plans to produce this as an single software or so, but of course it's possible to do that. Maybe if someone is interested, we're always happy to discuss a collaboration or something like that.
Okay, thank you, Mats. So it's time to play now with the Menti interlude. So welcome back, Daniel, for the last time today.
Yes, thank you, Philippe. We will now start the fourth and last session of the Menti. I'll be sharing my screen. Let me know, please, if you can see it.
Yes, we can.
Okay, perfect. So we will now start the fourth and final Mentimeter session, which focuses on communication and application. And I will be guiding you through the questions again. So a quick reminder for the last time. So to join this session, please go to menti.com and enter the code that is shown on the screen, or you can simply scan the QR code. Once you are connected, please tap the next button to start answering the questions. And like the last 3 sessions, you can answer at your own pace. There is no need to wait for me to move from one question to another. So as the last 3 sessions, the next 5 questions were the same. So if you're attending multiple sessions, if you already attended the previous sessions, only your first response will be recorded. Yeah. If you have already replied to the first 5 questions earlier today, you can simply tap the next button until you reach the questions that are specific to session number 4, which is the last one today. So we come back again to the first question: from which country are you joining today? So we can still see that we have a broad European participation from different European countries. Then the second question, we wanted to know from which sector do you work in? And we can see that the research and technical sector remains strongly presented with 87% participants coming from this sector, 3% from the industry sector, 8% coming from the institutions, ranking it second. And finally, some of you come from other sectors. Then we wanted to know your level of familiarity with uncertainty in geology. And we can see that 38 of you have an intermediate level, 31 have an advanced level, 30 have basic, and 13 are beginners. Let's now come back to the expectations. So we can see that the expectations were focused on exploring methods and tools to manage uncertainty. Then in the second place, with 27% of you expect learning from case studies across topics and countries. In the third place, 22% of you, their expectations were understanding the sources of uncertainty in 3D geomodels and maps. And then finally, 18% of you were expecting communicating uncertainty. And then if you selected other expectations, we wanted to know what was these expectations. So you can see here different answers and replies, like learning, broad overview, get to know GSEU and their projects, visualization of uncertainty, structural uncertainty, learning more information, to know more about the subject, visualization. So yeah, several comments and different expectations today and yesterday. Moving now to the 3 questions that relate specifically to this session about communication and application. So the first question, we wanted to know in 1 or 2 words, whose decisions are most affected by uncertainty in geological models. And as we can see on the screen, that mining companies are the most affected, but also geologists. And you also shared other decisions that can affect other stakeholders like consultants, economists. Yeah, different views. There is a range of actors here identified. Let's now look at communication approaches. So here we wanted to ask you to rank the following approaches for communicating uncertainty to stakeholders, with the most effective at the top, which is discussing uncertainty directly with stakeholders. And then in the second place, you have ranked embedding uncertainty directly in maps and model outputs. In the third place, displaying, so we can see it's moving. In third place, displaying the location and density of input data. I'll change it again, different views on this question. But yeah, in the last place, we have displaying the location and density of input data. And now we will move to the final question about the importance for scientists and stakeholders. How important are the following for scientists versus for stakeholders? And we can see that most of the suggestions are more or less important for both scientists and stakeholders, but specifically managing uncertainty in 3D geomodeling are important for stakeholders and scientists, but also integration of uncertainty in 3D geomodels into decisions are very important for stakeholders and scientists at the same time. So Thank you for your participation in this final interactive session. I'm sure that these responses highlighted the importance of aspects of how uncertainty is communicated and applied in practical life. We appreciate your engagement through this workshop, and this is the end of the Menti session. Thank you.
Thank you, Daniel, and thank you all for your participation. We maybe will come to that during the discussion. So let's move now to the last presentation before the break. This one is from Team Kearsey from the BGS, the Great Britain Geological Survey, and Tim is going to talk us about some lessons learned regarding uncertainty and the way they are communicated to the stakeholders.
Okay,
Tim?
thank you, Philippe. Right, I'll just share my screen. Just stick this into presenter mode. Is that working? Brilliant.
Yeah,
okay,
absolutely. You can
okay,
go.
so well, thank you for inviting me to talk. This is a talk that's coming from some practical examples where uncertainty has been critical to get across, particularly to stakeholders. In most cases, these are other scientists, as I'll come on to. And it's sort of how do we bridge the divide between uncertainty, which can be a very theoretical subject, and calculating and trying to measure uncertainty, and then turning that into something that is useful by other scientists or other stakeholders more widely. So again, I know we've had 2 days of this, but there are obviously multiple ways of measuring uncertainty in geological models. The first is the qualitative approach, and this does have some merit, and that's just essentially an estimate by the model creator. It's crude, but it does actually, there is some reasonable research to say it gives, if you have nothing else, it's better than nothing. You can use bootstraps. This is where you delete a proportion of your data, and this is things that I've used in the past to try and communicate uncertainty. So that's where you delete a certain amount of your data from the model, rerun the model without that data, and then use that the excluded data as a test. That works quite well if you want like a level of accuracy, but it's obviously quite intensive, and you need a lot of input data to do that in a meaningful way. And then again, as sort of highlighted yesterday, there are the more probabilistic methods. Information entropy is one of the main ones, but most of them are really factoring some sort of level of complexity of your surface against your data distribution and trying to say that often in a probabilistic way. The problem is often, we can put a lot of effort into these uncertainty calculations, but then when you talk to anyone else, they can't understand what you're talking about. Most subsurface people who are interested in the subsurface really don't want to deal with probabilities. They want plus or minuses. I know this is changing as geomodels become more prevalent, but if you're talking to people who are used to using geological maps specifically, they probably don't really understand probability and will struggle to integrate that into their use of that data set. Oops. So I'm going to take 2 case studies today. First one, I'm going to take out some deep geothermal work I've done, where it was critical to sort of to explain why uncertainty was really important to the stakeholder and make sure that uncertainty was built into any further work. And the second one will be taking the same methodology we applied here to a much more site scale or city scale model. So this is 2 pieces of work that I was involved in about 2 or 3 years ago now, where we were asked to estimate the heat in place, the deep geothermal resource of the large scale sedimentary basins, the deep sedimentary basins. So we're looking at 4 to 6 kilometers in the UK. And there were really two basins that really fulfilled this criteria. There's the lower Carboniferous limestone, which is in southern England and the Midlands, so around Newcastle, Nottingham, and Leeds, and then Devonian sandstones in under the Midland Valley of Scotland. So that's as Edinburgh, which is where I'm talking to you today, and all the way across to Glasgow. So these are our deep geothermal targets. But what we wanted to do was create some more accurate heat in place estimates of the potential resource down there, mostly to try and get interest from, particularly with the industry. And again, our government is increasingly keen to push geothermal as a green energy option. Sorry. So the challenge here is we don't have much data. We do have seismic data and well data for these whole areas. So these are the input data from the two report, or the paper and the report, where you can see, so the black lines are the seismic. There's a lot less for the Midland Valley of Scotland. There's very, very little seismic there. But even the seismic that we do have is probably not that good. So there are only a very few number of wells that hit the top of these target units, and even fewer that actually prove the thickness. Particularly in the deepest parts of the basin where we were most interested, we had very, very little data. Equally, the seismic, the historical seismic, was targeted at hydrocarbon targets, which are stratigraphically higher than our intervals of interest. So although we could use it a little bit, we didn't have well ties, and those well ties that we did have were obvious. We could tie them on the edges of the basin, but as we started to go deeper, it became very chaotic. So we built models. So we were building models using Aspen Skewer as it is now. Skewer GoCAD, maybe more. Some of you may know it a bit more as. This is a fully implicit workflow, and we're relying on the data on the higher strata to constrain the intervals and the. Sorry, I'm just trying to get the pointer up. And to constrain the strata of interest. So we can see here, so you can see the red unit there is the unit of interest, and then on the other one, the blue unit here. And in both cases, these were almost, the tops were just about visible in some seismic. There was very little well control, so it was very much relying on the strata above to essentially provide that control for the geology of the target. However, obviously there was extremely high uncertainties on both of these models. So how did we deal with this? So we did look at trying to do bootstrapping, but we didn't have enough data to do that in a meaningful way. We did try some probabilistic approaches, but again, these were models were designed to try and to inform heat in place models, which needed a plus or minus. So what we ended up using was model well mismatch. So some of you may know the sort of concept of overfit and underfit. This is so we got in this image here we've got control data from a whatever data set. A correct fit would be a best fit line through that at the scale of the model. If you overfit the data, you can, so this is fitting the data exactly, you almost create noise, and that can actually also cause problems in your surface, particularly in an implicit algorithm. You end up with these little spurious spikes where by overfitting to the noise in the data set, you're actually disturbing the interpolation elsewhere. And when we overfitted to this data, because of we had such low correlation, so we had so little data, we ended up with really, really spiky surfaces. So that's why we ended up using a much slacker fit. But then we realized we could use the offset of that fit as a proxy for uncertainty. And this is what we did, and this allowed us to, we segmented the model based on the areas of interest. and calculated based on the mismatches to the wells. So we didn't tie it to wells, we just used the well mismatch. And that gave us a plus or minus of depth uncertainty, which obviously also then translates to thickness as well. That was critical because we then wanted to develop, we wanted to use these models in thermal model, heat in place models, and we could integrate that plus or minus into the general calculations, because the heat in place calculator we were using allowed for plus or minus values for other inputs. This meant we had a better control on the resource model, and when we developed the actual maximum thermal models here, this is actually integrating the uncertainty on the depth into all the other uncertainties, like the uncertainty of porosity and permeability, uncertainty of the thermal and the knock-on effect on the geotherm, all of these things. And we could develop it, and that meant that the outputs and the values that we created here showed quite a robust range of values. The other thing we could use was, obviously people are now starting to use these models to actually try and cite geotechnical, to cite deep geothermal boreholes. And we have that ready estimate of going, okay, well, we know in this area there's a really, really high uncertainty of the order, in some cases of this model, thousands of meters. You need to build that into your drill plan, or you need to shoot subsidiary data. And then this is actually how we've, when this question has come, this was actually the lead in to saying, right, we need the client or the person who was interested in the model to shoot subsidiary seismic data to better constrain the data, rather than just using our value as read and then drilling a hole and then going, it's not, the hole needs to be a kilometre longer than we thought it was. So that approach worked quite well. It was a little bit of we needed to do something, and we were being constrained by the actually the heat and place algorithm, which or calculations which prefer plus or minus and couldn't cope with p-values. But this methodology seems to be quite powerful, so we've used this elsewhere. So another project that we've finished last year was a completely different scale. This was looking at groundwater flooding in coal measure strata in a place called Newcastle Gateshead, which is just in the northeast of England. And there they have local issues with groundwater flooding, breaching the surface and causing localized flooding. And this was in an area where we had historical mining, we had quite a complicated quaternary succession, and again, it was interesting. We were keen to try and make sure that, so there's a lot of complexity in this strata, and we wanted to make sure that that complexity and the uncertainty inherent with that complexity was pushed through into the any estimations of these areas where there may be groundwater flooding. So in this case, and this is kind of just to show the sort of change in scale here, this was a model that was 20 kilometers by 15 kilometers, relatively small model. We probably had more boreholes with this model than we had with some of the models I've just been talking about. So we had 173 boreholes. And we also had, and this is a really useful data set if you have it, we also have 3D mine plan data, which is, there's an example here on the shown on the slide, for 7 underground worked coal seams within the strata. So a huge amount of observational data. But again, there's still a lot of noise in this data. There's uncertainty with the positioning of mine plans. This is a lot of, because they were historically done in feet, fathoms, and inches, and they would have been using a mine datum rather than the land surface. It's an urban area, so the land surface has changed a lot. And a lot of the boreholes we were using were nearly 200 years old, and therefore the Z positioning on the start heights on them comes with that sort of level of uncertainty. So again, we built the model in the same situation, and using the same software, so against GeoGoCAD, same workflow, the implicit workflow. And again, we didn't overfit the data to the borehole data, because we realized there is this inherent noise within that data set. These surfaces were then to feed into groundwater flooding hazard map that was being developed by another agency that we were working with on this project. And we could provide those surfaces with that plus or minus. And that was really useful for the person developing the flood hazard risk map, because that was the Z control on these surfaces was really critical. They were using sets of cutoffs. If we could say, well, there's like in this case, it's like a 5 or 10 meter uncertainty on some of these surfaces, they could build that into their estimates, their flood risks, so that we hopefully provided a more robust flood risk map by also communicating that uncertainty in a method that meant that it could be then integrated into the output that was being developed by our partners in the Environment Agency. So that's a bit of a whistle-stop tour. I just hopefully really wanted to highlight that many stakeholders really want to know that uncertainty in terms of plus or minus. That's from these two examples. I think that was really the main take-home message. Yes, probability is a useful way for us to try and understand uncertainty, but really stakeholders want to have that numerical value. One of the ways you can generate that, and again, it's very much dependent on the software you're using, is not fitting your model directly to the markers, and then using that well mismatch as an estimate of vertical error. Yes, there are more robust ways to do it out there. Yes, there are more sort of theoretical ways to do it out there, but if you just want something that you can very quickly explain to someone using the model, a plus or minus, that is really, really useful. And again, because you're talking in Z terms, and often this is why, if you think about it, people are using 3D models because they're interested in where something is below the surface. By providing it in that data rather than a probabilistic value or an uncertainty value, it really helps embed the uncertainty and communicate that uncertainty to other stakeholders. So I hope that's been interesting. I'm more than happy to take questions, and I'll leave it on this slide. These are the reports that I have been referring to. So all the work that we've been referred to has just been published.
Thank you, Tim. Thank you for sharing this with us. Is there something to add to Tim's presentation? Some question? It was quite clear and very informative. Stefan, please.
Yeah, look, I like that presentation, Tim. And some of the things that came up yesterday about measuring uncertainty and decision making, and the uncertainty quantification being dependent on the decision, you seem to have sort of either solved that or lucked into it, because the problem that you were solving was, particularly in the water case, is the water going to flood in this area? So the uncertainty was directly mappable to the decision. And so that made everything very, very effective. It's not always the case that it's that simple. And the depth thing that you mentioned, with the location of where something is in the subsurface is not always related to depth. So the lateral location of faults and things is of interest. But it was a very good example of how matching the uncertainty quantification to the decision that's being made everything very, very clear. Great work.
Thank you. Again, I think you hit the nail on the head of what I was trying to convey there. I mean, the two examples I was giving were obviously depth related, and that worked really well. Thank you. Any other questions?
Yep, and another thing. Yeah, we have a question from Anika in the chat. Would this workflow work in more undulating or scattered formations if you don't have much input data, of course?
I think it very much depends on how you're calculating your surface. So implicit modeling, because it's obviously using all of the available data, this is kind of one of the things that falls out of that. I mean, I'm using Aspen Skewer, and you can use the well mismatched table to provide. This is essentially what I've been using here. It very much depends if your modeling is. You could probably do this as kriging, because that obviously there's the kriging variance can come out of that. If you're using a slightly more direct triangulation or using a geostatistical methodology, that obviously becomes harder. I think that, again, coming back to the previous questioner's comment, I think that what is really useful is making sure that you match your uncertainty to what the people who are wanting to use that model want to know.
Yeah, and I can ask a question about that as well. And from your experience and the various stakeholders, do you think that they all expect the same thing in terms of are they concerned at the same level about uncertainties and so on in the?
That's an interesting question, and I think I probably need to unpack it a bit. I think it very much depends on the level of person. So if they're using a model as if it's a geological map, that they may not, and again, this is based on personal experience, they may not even realize there is uncertainty associated with those units. As you move more and more to more professional people, so people are actually either using the outputs of the model in a forward propagation, that discussion becomes easier. So I think this is one of the challenges we have for coming from as GSO, so Geological Survey organizations, is our experience from BGS is increasingly we tend to create models to answer specific questions, deep geothermal, urban, and two examples, because you can then very nicely lock it into a specific set of stakeholders, and you can then make sure that you can describe the uncertainty more widely to them. I think trying to do it at the sort of national scale level, it becomes challenging. Trying to be as agnostic as we are with the geological map historically is, I think, more challenging. And I mean, we obviously tried this a few years ago, and this was kind of why the only people who were really interested in those national scale models were sort of the big scale screeners. It was the people who were wanting to know where to put a radioactive waste store, for instance, or very, very crude large architecture stuff. But very, very quickly, as you start to work with, and these are often other agencies, they then want to know much more specific information, which allows you to then tailor things to answer that question.
Okay, and maybe the last one from the chat from Guillaume about the question of faults. Taken into account faults, especially for uncertainties.
Okay, so there's two things, and again, unfortunately, I didn't have the fault story on both of these is really, really fascinating. So on the deep model side of things, yes, a lot of that uncertainty is the fact that we know there are faults down there that we cannot see. I think one of the big challenges we have at trying to make those predictions at depths where literally really don't have the data to make that in a meaningful way is some of that Z uncertainty, that vertical uncertainty, is the fact that we're trying to draw it like that and it's actually segmented by faults. And there were parts of the model where we knew this was the case. On the other side of things, we have the other problem with when we're talking with the urban model, is we actually probably had too many faults shown on our maps. So historically on coal seams, the miners would have mapped any fracture, even with a displacement of yay as a fault. And actually the big faults sit in the gaps between the mine workings. And until we started to build the 3D models, we really couldn't actually quantify the throw and offset. You can do it a little bit with the displacement that you can see on the map, but because we had fantastic 3D data, we could actually show the displacement, and interestingly, we get the damage zones, which we'd use the gaps in the mine plan information to hide. But that meant that we could actually segment the faults from those faults which have a throw of I can't remember what we used. I think it was about 100 meters, and that's what we modeled. So actually, in that model, we had on the map, I think there's something like 100 faults shown, and we actually only modeled 4 of those because only 4 of those had a significant displacement enough to have a damage zone. Most of the rest of them were essentially the noise on that uncertainty. So a lot of the local uncertainty is the fact that there are many little minor faults in this strata. Now we did have the advantage, and I know this is something that many European countries don't have. We could see this stuff on the coast, so we knew this was what was going on. So we could use that in our sort of analogy, explaining to the our colleagues in other agencies why what was happening.
Yeah. Okay, so we can conclude your presentation on these words. Thanks again, Tim. So it's time for the break now. We meet again at 20 to 4 as scheduled in the program for the 2 more presentations and then the final discussion. See you in 20 minutes. Okay. So time to start the last part of this session dedicated to communication and applications, and the last part of the workshop itself as well. We now welcome Jan Franěk from the Czech Republic Geological Survey. Jan is going to tell us about the beam. We already seen something about that at the beginning of this session, and the uncertainty calculation, especially in complex regions. Jan, I can see your slide.
Great, good afternoon. Thank you, Philippe, for introducing. Let me describe. I hope you can hear me.
Yes, I can hear you, but a bit far away, in fact.
Let me check out. Is it better?
Oh, yeah, much better, yeah.
Perfect, please. Thanks. So I'd like to describe you how we are in the last several years quantifying uncertainty of our geological models, which we create manually, and how we incorporate them into BIM exports for their further use by the people who actually pay us for making the models, usually for some construction site development. As you can see, the geological map of Czech Republic, it is quite complex, built mainly by crystalline basement, and which means that we have almost never enough data to create the models in the implicit way, but we rather have to create them manually or in explicit form according to our extensive field knowledge. And the uncertainty in the geological models is involved in our case, not only to make the models, let's say, more useful for the stakeholders, but also to protect ourselves a little bit, because to involve uncertainty actually means a little bit disclaimer for us, for the model that we supply for the constructions, to say that we are not entirely sure whether the model is correct or not. If you look on this example of a model of, let's say, 12 times 10 times 1.5 kilometer, you can see that there are many source boreholes in these yellow rigs. But if you strip off the geological map, you see that the extent of the boreholes regarding the depth of 1.5 kilometer of the model is really ridiculous. And majority of the model is really just geological imagination based on the map and some structure measurements around. And even if you look on the typical countryside in Czech Republic, even the surface geological map is not like from some 100% exposure, but it is rather a geological interpretation of some debris mapping and so on in such an environment. And even some outcrops which are not that common, are not big stone walls like in the Alps, but rather small, a bit ugly outcrops, either in natural or some artificial road cuts and so on. Which means that, as I already mentioned, we create the models mainly manually, And we need to employ our extensive field experience and also broader regional studies, some papers or reports which were published from the region of interest or the surroundings, which are simply things that cannot be gathered in some database to be later passed for some implicit modeling on numerous runs of a parametrically defined model, which also led to the thing that we gave up some attempts to get to some rigorous or absolute uncertainty value calculation, and we produce only relative normalized uncertainties of our models. And let me introduce the BIM, despite it was mentioned already a little bit. BIM, or Building Information Modeling, is in fact a concept how to handle construction data. And it's something that is developed very much in last years and offers wide suite of software tools available, either for free and simple ones, or expensive and much more user-friendly and robust ones that can handle also very large models, including our geological ones. And that can these softwares can in principle handle three-dimensional geometries of various types, including many attributes. In fact, all what we needed so far from the geological models to involve was possible to do somehow to the BIM software suite, usually using the IFC open data format that we use for the transferring of the models. And of course, because we supply the models usually for some designers or architects, then we must do it in accordance with some ISOs or some other conventions that are respected by these non-scientists, or at least non-geologists. And let me first describe how we pass the geological models into BIM, because it's important to understand later how we incorporate the uncertainty into it. So after some initial attempts, we are coming with a twofold approach. First, we discretize the models into a regular net of voxels, let's say 10 times 10 times 1 meter in size, which allows us to populate the voxels with individual variable values all across the modeled volume. And this we do directly from the modeling software by some export, which we then rework in through some Visual Basic scripts in Excel. And from Excel, we export it by our own script to the IFC data format. And the other way is production of quasi-homogeneous volumes plus some unclosed meshes, like let's say groundwater table or fault planes and so on, which we first export as meshes from the modeling software. Then we manually somehow adapt it to make the volumes watertight and so on, and generally to make the topology correct in Blender software. And then we export it to IFC format using the Blender Bonsai extension, which is free of any payment so far. Which means that each of these objects has a very precise representation of the original geometry, but is only a single object with populated by single values. This is how it looks in reality. On example of one model, this is a construction site, or future construction site, let's say of 2 times 1 kilometer size, and a bit exaggerated. It goes to a depth of less than 200 meters. And these are the individual quasi-homogeneous blocks of some metamorphic rocks and quaternary and tertiary deposits lying on top of that. And here you can see from some small portion of the model the discretization of the voxels. So these two derivatives of our native model from the Move software are exported as IFC files, which are totally independent. This is one file with meshed volumes. This is another file which is made just of bricks that describe lithology and some other parameters derived from the geological model. This is another example of IFC model from our colleagues from Czech Technical University, which was involved into this construction site. It's something, of course, totally different, where you can see all these engineering objects from the interior of some building, which also carry some normalized or systematically saved value that are important for the designers and so on to carry the building and the architecture of that. And all these models can be then in the BIM softwares quite easily combined, as you can see on this example. Here is one part of the construction site model that we could see before, which is voxelized. Here is the small building, which you can see in more detail here in the other parts, where you already see that in the BIM software, you can, in this combination, nicely model or evaluate how the building affects its underground when the underground voxels of the geological model are, let's say, populated with some rock strength or some other geotechnical parameters, which was actually done by some geotechnical company which followed us in the modeling process. And here you can see the detail of the pillars, how they fit into the quaternary, tertiary, and some weathered crystalline in the subsurface. The other example of a bit larger model, again in the BIM software, is given on this slide, where you can see a combination of our geological model. This is actually a granitic massif in the red color, cut by many faults, into which the engineers have designed some large excavations to about ½ kilometer depth here in the granitic massif. They populated this plan of underground channels with some engineering parameters, and the same did we for the rock and faults. It means we ascribe there also the lithology, let's say some estimate of uncertainty or of the lithology model, and then everything was quite easily combined in some cloud environment of the Trimble Connect software, as you can see here, where simply the voxel model in the IFC format was uploaded together with the with this volumetric model in IFC format and with the engineering model of the subsurface excavations in the IFC, and just by simply clicking on the view, everything was visualized in the cloud environment. It means for the whole working team together, either the engineers or geologists or whoever else would be interested, theoretically even public, if it would be allowed to access it. And now let's get to the way how we actually involve the uncertainties into the geological model. We came up to strengthen them as much as possible. We use the three ways of how to put them inside. The one is that in the voxelized form, we have calculated uncertainty of each voxel according to our paper, which we published just a year ago, but the calculation that we developed many years ago, and which is based on what was already mentioned. It means the combination of entropy and complexity of the geological model with regard to the input data and their reliability and proximity to each voxel, which brings a scalar property to each of the voxels. Then second way was some classified expert estimate of uncertainty for each, which was given one for each of these quasi-homogeneous meshed volumes. And it was involved as text property of each of the watertight meshes. And the third indirect approach was that we developed scripts that allow us to involve all or almost all the source geoscientific data that we used for the modeling into the BIM or the IFC export, so that even the engineers and other users can directly watch it in the model and guess by themselves how well we were constrained in some parts of the model. While this third is mainly for watching, the first two approaches serve for active user work with the model. In particular, they were used by the designers for filtering visualization of in the BIM software. For example, they had filtered out the voxels which or the volumes which were having the high uncertainty, or they made them, let's say, more transparent to pronounce better the parts of the model which are better reliable. If we And here is the first approach in more detail. It is just citation of the paper where we describe how we did the calculation of uncertainties of the voxelized model. Basically, if we follow this algorithm in some Visual Basic script on the exported voxelized model, we come up with some 3D grid where each of the voxels carries one single scalar value, which is normalized between 0 and 1, which describes some relative uncertainty in the particular brick of the model. And here you can see it in the top, in the bottom right, as it is imported into the BIM software, where you see already very much detail of the voxelized model. Like each of these voxels is 10 times 1 meter large. The gray is, I think, anthropogenic. The pink is some migmatite, let's say. And in the property set CGS Geology in the BIM file, you can see that there are basic parameters like lithology, then lithology credibility, or it would be, let's say, high credibility is like low uncertainty. And then a level of weathering of the rock in this particular volume estimated by our model, and then the weathering credibility as well. It's just a funny thing that the stakeholders in this case didn't want to call the parameter uncertainty, but credibility, just for better psychological feeling of the of the value. And so then some other parameters that were designed after discussion with the stakeholders to better classify the model in their software tools. And you can see again snapshot from the Trimble Connect cloud web environment, where you can see another model discretized into voxels, and you can again see that each voxel bears the CGS Geology property set, where a part of lithology, there is also the lithology credibility value, which shows how much you can relatively believe the particular part of the model. And again, you can easily visualize, switch on, switch off these elements and inspect all their properties, including the engineering elements. So for the second approach, it means how to ascribe credibility or uncertainty to the watertight volumes. We finally decided to use some classification based purely on expert estimate from some letter. It's something like marking at school from letter A, which means perfectly grounded body of rocks, which is well described in the source data, up to F, which is totally a hypothetical body that is based just on some indirect indications, and we are really not sure about how big it is and which orientation it carries. And you can see that this uncertainty or credibility is present again in some CGS Geology property set described as lithology source property and weathering source, graded here both for C. It means partly relatively well defined, but with some amount of uncertainty. So, and the third and last way how we incorporated indirectly the uncertainty was actually the integration of primary geoscientific data into the BIM. Here you can see example of boreholes and some geophysical or geological profiles. For the boreholes, we made such a visualization of lithologies, tectonic disruption, and weathering of the borehole in some triple-sided prism. And while the head of the borehole bears a link to the Czech Geological Survey database, where you can open a map and basic data about the borehole, and it also bears a link to a PDF scan, which is nearby the IFC file, where you can open the original borehole description from the time of exploration. And the similar is done for the geophysical or geological profiles in this case, where if you click on the geological profile, you can access the PDF scan quite easily to see how it is grounded. And the last slide shows just that there was, even on this small office building, there was already some money saving, because when engineers have projected their original position of the planned office house to our geological model. They found out that when they shifted, like, let's say 20 meters aside, they will reach some much better rock environment where they will need shorter pillars to ground the building. And by that, they saved almost the price that they paid us for the whole model of the whole construction site. So thank you for attention. That's all for me.
Thank you, Jan. Thank you for your presentation. Have you some question for Jan? Yeah, I can see one in the from Guillaume in the chat. It's about the principle you use to estimate local uncertainty on voxel models. Can you a bit develop on that?
Well, basically, it was calculated based on this paper which we published 1 year ago. So at best, if you look at this, I can maybe send. I think it's open access, so I can send some link to the chat later when we finish. But basically, first we evaluate using. I'm not a mathematician. It was this guy, Mr. Staněk, who did the calculation. But use the entropy evaluation, let's say complexity of the geology in the surroundings of each voxel, as suggesting that the more complex the model is in the voxel surroundings, the less probable it is that we are correct in that part of the model. So this is how we produce the initial uncertainty, let's say. And then we increase the credibility or reduce the uncertainty in the vicinity of the source model data. But if I would have to go in more detail, it would be for another presentation, yeah, really, unfortunately. So I suggest, if you are interested, please have a look at this paper. And if it is not clear, which may happen, of course, we are not native speakers and so on. So please write me email and I will try to explain.
Okay, thank you, Jan. There are a couple of more questions in the chat. Maybe you can answer directly in the chat. I see it's 4 o'clock. It's time to go to the last presentation. Thank you again, Jan.
Welcome.
And the last presentation is from Steve Tyson from Industrial Mathematics and Physics company, and Steve is going to develop about the power of images, I think, related to uncertainty.
Yep, that's right. Can you hear me?
Yes.
Okay. Just give me a second. Okay.
So it's in the it's not full screen. It's in the presenter mode, so we can see the other slides as well.
Okay. 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 Does that look right?
Yes, I think better. Yes, it's okay. It's okay now. Yep, you can proceed. Thank you.
Okay. Okay. So there's not much geology in this. It's probably quite a light presentation. So let's hope it's interesting. The motivation behind this is because, in my experience in the oil industry, once somebody had created a geological model, everybody in the company believed that that was the reservoir. And it was very, very difficult to change people's mind about that. And particularly if there was some structural changes, it was very difficult to get the senior management to believe that this was a modification. So what I think is that if uncertainty is not actually included in the visual, then you're going to actually start creating conflict. And I've noticed that your entire visual system is programmed to make things real. So the thrust of this talk is to show you how your brain makes things real. Interestingly, artificial intelligence vision recognition is being trained to do exactly the same things that we do in order to make things real out of what we see. I've got a bit of help here from some experts in visualization. So Surat, Monet, Brack, and of course, Wiley Coyote know a little bit about visualization. So here is the oldest map of Australia that I could find. It was drawn in 1753, and the cartographer was very honest because on the east coast, which is clearly not the shape of the east coast of Australia, he wrote in French. He wrote, "I think that Van Diemen's Land, Tasmania, could join up with St. Esprit's Land, which is Cape York at the north of Australia." So he was actually being honest in his uncertainty, and he was drawing attention to the fact that he didn't actually know this. Now, how often do you actually see that on maps? How often do you see that sort of "I don't know" admission in anything that you see in terms of visualization? The other thing about visualization and uncertainty is that I think that we need some sort of narrative for how uncertainty is presented, and the sort of clearing of the fog is the way that I think about it. And so if you look at this image, there are some clear data points which are represented by the lights, and they're very easy to locate. And then there are some blurry shapes. This is probably the sort of thing that Google Capture would expect you to see a traffic light in. What we're actually looking at is real, and we just can't see it very well. And the decisions that we need to make help us sort of identify the level to which we can be uncertain. And there are two questions that we could ask here. One is, am I seeing one big ship or two smaller ships? And that would affect the way that I navigate it if I was in another ship crossing this piece of water. An alternative question is, are these objects friends or foes? Which is a military engagement type of question. And it's not sufficient to just simply determine whether it's one big ship, like a battleship, or two smaller corvettes. You have to actually identify that it really is an enemy ship. And the level of uncertainty that you could live with for that decision, and the parametric forms of the uncertainty are very, very different for those two questions. This was something I think that Tim in his talk was actually quite fortuitous, because his decisions were really quite simple. So there's a concept of image anchoring that I've seen, as I said, in oil companies. Once somebody has seen an image, it becomes the reservoir. So here's a typical 3D image from some sort of oil company asset. And we very commonly see these reports. And it does occur to me why we actually do this, because it doesn't really add anything to it. I guess junior geologists or petrol jockeys put these images in their reports and presentations simply because they can. It really tells us very little, and it actually starts the process of misinterpretation, because there are two sort of faulted areas in this model, which will persist in everybody's minds for the whole duration of that asset. Once an image has been seen, you can't unsee it. Your mind is programmed to make this real. As an observer, you can handle parametric uncertainty where the color changes, but you cannot manage structural or shape changes. I'll go into this a little bit more later on. So the solution to this is, do not ever present a 3D model in your communication without guidelines. And I was tremendously encouraged by the fact that most of the presentations in the conference relied a lot on 2D images. I wasn't expecting that, but I was pleased to see it because 2D images are much, much easier to understand in terms of uncertainty. And 3D images become real. 2D images don't. Okay, this sort of perpetual contamination is something that we need to sort of stop at source. What you need to consider is that your 3D model has some structural and property uncertainty. So if you take a screenshot and somebody sees this, this starts the perpetual contamination. Once it leaves you, the screenshot that you put in the presentation has no metadata that will inform anybody of its shortcomings. The presentation about the Spanish fires, I know that was a 2D mashup by an extreme right-wing organization. But once somebody has seen that mashup, then it's difficult to unsee it. So it occurred to me that advertisements must show warnings if the product may not be exactly as advertised, primarily to avoid litigation. And I think that some of the geotech presentations that we've seen have highlighted the fact that as consultants, they're concerned about litigation. They're concerned about risk sharing with their clients. And so here's a typical product. Most images that you see in hamburger restaurants will have something like this on the poster. It says a serving suggestion, illustration purposes only, the product may vary, the images are simulated there. I've never actually been served a burger that is this tall, and I doubt if anybody has. There are good legal reasons for these warnings. If we put a similar set of warnings on a 3D model, we could say that this is a subsurface asset suggestion. It's for illustration purposes only. The asset geometry may vary. These images are simulated. The approved use is limited to flow simulation or volumetric calculations or whatever. I actually think it should include a use by day. And there would be good legal reasons for putting these warnings on any communications that have these images. Okay, let's have a quick look at how we actually interpret images. We are trained to create reality out of whatever we see, and the Impressionist painters, of course, created paintings out of dots. And when you look very closely, you see all these dots, and when you stand back, you see an image, because your brain works like that. If we consider parametric uncertainty, where we change the color of something because we're changing the parameters, we can handle that in our minds because we're used to seeing things change colors. And Monet did this spectacularly with his series of paintings of Rouen Cathedral. In all of these pictures, you can clearly see that it's a cathedral, and you can clearly see it's different colors, and you can interpret that as different times of day, and it doesn't mess with your head. Structural uncertainty does. And so this is the structural uncertainty in art. Braque, of course, and Picasso created the Cubist movement. And you can see that the structural uncertainty, or the multiple structural representations of different views of objects, create confusion in your mind. So a key point in visualization is that parametric uncertainty is easy, structural uncertainty is difficult. So we can tolerate property uncertainty, we resist structural uncertainty. Color changes are easy because the object's identity remains stable, the boundaries don't move, its topology doesn't change. And the brain sees this as same thing, new state. Same thing, different times of day. Same thing, different life. Same person, different colored clothes, okay? This is cognitively cheap, and it fits in our object permanence model. Okay, shape locations and changes are disturbing. So when boundaries change, when volumes change, when the topology changes, when the spatial relationship shifts, now our brain is looking at this and saying, is this still the same object? And that is computationally expensive for us. And we've crossed from a parametric uncertainty to an ontological uncertainty. Is it the same thing? So previously we're thinking, is this bird blue? And now we're looking at the structural issue, and we're saying, is it a bird or is it a plane? Much more computationally difficult for us. So I think what we need is some sort of rules for visual integrity. And I need some sort of inspiration for this. Now, Chuck Jones was a cartoonist for Warner Brothers with Bugs Bunny, Wile E. Coyote, and the rest of the gang. And here are some of the laws of cartoon motion. I won't read them all, but some of them are fun. All principles of gravity are negated by fear. As speed increases, objects can be in several places at once. Any violent rearrangement of feline matter is impermanent, and so on. Now, these are not actually trivial. They're not arbitrary. Chuck Jones actually thought about this, and they actually allow us to encode deeper animation principles such as anticipation, exaggeration, timing, and psychological causality. So cartoon physics runs on knowledge and emotion and narrative time and expectation, not the physical principles, force, mass, and inertia. And does that matter? Well, of course it matters, because it's part of the narrative. It's part of your explanation about what's happening. So if cartoon physics has laws to clarify the communication narrative, could uncertainty modeling have laws to clarify the communication of cognition? Well, I think it can. So here are my first draft of some laws of uncertainty perception. Okay. I won't go through this list as the list, but I'll go through one at a time. So a model with unknown regions will be perceived as complete unless uncertainty is made visually unavoidable. Why? Because we auto-complete. If there are gaps, we fill those gaps. If you show a surface with a gap, observers will mentally fill that gap. So if uncertainty matters, it must be encoded aggressively. Observers will anchor on the most visually stable region. And if you show them multiple, if you show them in an early part of the project, your model, and it's the same model and it's structurally the same model in the early phases of a project, and then something changes and you come up with a different representation later on, you're going to get a lot of pushback from management. So the most visually stable geometry becomes your mental reference frame. This is the anchor. And you need to be aware that there is a visual anchor, because it's very, very hard to reset that visual anchor. Uncertainty that hasn't been explicitly encoded will be interpreted as precision. Silence implies confidence. Okay, if you draw a clean edge, observers will assume it's known. Okay, the default is that if you can perceive it, then it's certain. Now, that's a scary statement when we're talking about uncertainty, because if you can perceive something, that becomes certain, and it's very, very hard to overcome that. Your mind finds it very, very much easier to interpret a wrong coherent model over a correct ambiguous one. So if you're given a single clean but wrong service or a probabilistic cloud of truth, most people will trust the clean surface. So clarity beats accuracy when it comes to perception. Sharper the boundary, the stronger the implied lines. So crisp lines, high quality 2D, high quality 3D graphics imply confidence and authority. Blur and lower quality images imply doubt. And when I was teaching a few years ago, I asked the students which would be a more preferable map. One that was written by a young graduate who was a computer jockey who could create a beautiful map on a hard copy map, or a hand-drawn map from a 30-year-old geologist with pencils and crayons. Now, when you frame the question like that, they know that they know that you want them to say the old guy. But if you don't know the source of those two maps and you're presented with the hand-drawn sketch and the high-quality map, most people, particularly outside of our domain, will take the high-quality map. So image quality, particularly on hard copy, is knowledge. We think about transparency to indicate uncertainty, but transparency is hard to measure by eye. So transparency implies possibility, not probability. If you show a translucent region, observers will assume that it might be here, but they find it hard to say there's a 63% chance that it will be here. So the opacity is useful, but it only communicates plausibility, not distribution. Multiple overlay possibilities are perceived as noise unless structured. Now, the challenge when it comes to the structural stuff is that if you show large numbers of multiple possible structural models, people won't see probability, they'll see chaos. And so you need to be able to talk your observers through your portfolio of possible structural models. And this comes to the question that Guillaume put in the chat recently. The whole ensemble of models that you present to the observer must be presented in a way that they can understand those models. You can't just chuck random models at people and say, these are all the structural possibilities. I think that you need to organize those because the cognitive load of understanding different structural models is huge. So the visualization structure must organize the multiplicity of your structural models to assist the observer. Discrete alternatives are easier to understand than continuous uncertainty. We know this. So if I say 3 possible shapes, is much easier to understand than a whole sack of different options. So the quantization aids the comprehension. And so if instead of having a large range of structural possibilities, you can come up with some sort of concept around type curves or type models and variations in some sort of clustered domain. And you can say, well, this is a type A, B, C, D, E, F model, and these are the main things that we're considering. There may be variations around those, but these are the main concepts that we're working with. That is understandable.
Steve, I'm afraid it's time to come to the conclusion now. I'm afraid it's time to come to the conclusion, yeah.
Okay, I'll run to the conclusion. I'll have to skip a few of these. So these are conclusions. Okay, models become real once we create a visualization. So we need to be really, really careful when we share visuals. Property uncertainty is much less challenging than structural uncertainty. 2D images are much less susceptible to anchoring because they're not 3D. And we're used to seeing 2D representations of reality, which our brain doesn't turn into 3D. And we should present and maintain multiple structural options to avoid anchoring. Okay, thank you very much.
Thank you, Steve. Thank you. It's very interesting. I'm sorry, but maybe we can come back to some slides if needed. It will depend on the discussion on the discussion as well. Is there anything to discuss with Steve regarding this proposition? Maybe one of the way would be to blur our 3D model somewhere, or to to make some creepy images. Yes, Guillaume.
Yeah, I agree. I completely agree with what you said, Stephen. It's very important to try to visualize uncertainty at the same time of the average model. We actually worked on that a couple of years ago with Thomas Viard, And so I took a screenshot of his computers and geoscience paper where we tried to overlay color for the average and texture for the local uncertainty. And so we found that as one of the most convincing way to visualize this. Now, if you think about blurring, it's tricky because you have a number of visual clues in perception. And so if you have a really smooth field and you blur it, the blur will have no effect. I agree with what you said about transparency. It also depends on the background. And so we found that this kind of texturing or noising, adding some texture, was one of the most visually convenient way. But I haven't checked the literature on this area for quite a while, and there's probably some other new things with computer graphics that can be done in that respect. Where I would tend to, I mean, I agree that the movie of realization is disturbing visually. There was one thing that was used by some guy and by Pierre Thor at Total Energy a couple of years ago, who was doing gradual deformation to try to move smoothly the structures, which make it a more continuous movie rather than a random animation with unstructured things. So that was visually more pleasant. But to me, the animation is more to convey a sense of that there are uncertainties rather than locally quantifying the uncertainty. And the main use is in uncertainty propagation and running simulation on the model. So what I meant in my comment before was not for visualization purposes. It was mostly for quantitative uncertainty visualization and propagation of uncertainties to nonlinear processes.
Thank you, Guillaume. There are some comments in the chat. Chris said that 3D model is often best used in 2D slides in a geological section in a way, or vertical or horizontal or whatever. Some funny comments in the chat. Have you other comments for Steve on his presentation? If not, so thank you again, Steve. And now we can move to the last moment of this afternoon and this workshop and the final discussion. So maybe before that, if you have some, so yeah, you can turn on your cameras if you want for the discussion. If you have any more question for the presenter of this afternoon, it's still time to ask if you wish. So we had the presentation from Santiago regarding this what happened on the social media with the publication of this map. We have something about infrastructure project from Mats. I think Mats has to leave. He already left, I think. And then we had a team from BGS with some sharing some lesson learned in the communication with the stakeholders. Jan regarding the beam and the use of uncertainties within the beam, and Steve we have seen with this power of images, so it's more correct to say the power of brain looking at images.
Concerning perceptions, the last presentation, I want to say that all this is all standardized. There are standards for report forms, for geological information that is given. For example, we have ДКЗ, Державна комісія по запасам, yeah? Even in our country, no, not even, it's all standardized over the world. So perception should be based not on what stakeholder wants to see or do not want to see. We are working by standards. This is our credo. No other way. If we are accredited, scientists can, yes, they can work for imagination, yeah. We in geological company and test laboratory, we rely on standards, standards for methods, standards for classification. In other way, so we could not compare information between between each other. That's the pillar of the building industry standardization of materials and raw materials.
Yeah, thank you, Dmitry, for this comment. Something else to add about that? Honestly, I think I've never seen the use of blurring to present uncertainty related to 3D geological model, either in 3 dimensions or 2 dimensions. I don't know if you already saw something like that. If you already seen that. But blur could be a way to maybe easily give the impression of uncertainty, as it was demonstrated by Steve in the previous communication. Yeah, Guillaume?
Yeah. No, again, I mean, intuitively, that seems like a good idea, but when we tried, as I said, it collides with the texture. So if you have sharp bond, like maybe for structures, you could try it, but blur will only have an effect when you have some sharp features on your input image, the non-blurred image. And so that's kind of makes the whole thing a bit challenging. I'm trying to find a Thomas thesis because there's much more to what is in the paper. I'm going to try to share a couple of screens because he made a number of experiments there, but they did not go through the peer-reviewed publication because we did not have the time.
Yep. By that time, maybe Charlie wants to say something. Charlie?
Yeah, thanks. Well, on the topic of blurring, yeah, for uncertainty visualization, well, another option, I'm not sure if this has been mentioned or not, but if you're viewing on a computer screen, say, or in anything that can be represented as a raster, then for each pixel or each voxel, say, you could just sample that from a different model. Like, so if you've got an ensemble of 30 different models, just randomly sample each pixel from one of the models, and the certainty will become apparent when the models are in agreement, because then you'll have a visualization that looks consistent, I suppose. Whereas where all the models are in disagreement, then it basically just ends up looking like some kind of static fuzz, a bit like the fog that Stephen was on about.
Yeah, and talking about voxels, maybe a way could be as well to have different scales on the voxel. When you have a very good accuracy, you may have very little voxels, and when it's like much more uncertain, bigger voxel, for instance,
maybe
it could be a way as well.
Yeah, it could be.
Yeah, Stefan.
Yeah, I think that you've got to be sort of careful on that. So let's imagine that you've got a bunch of different shapes, for example, and then you sample those onto a voxel, and so those points that are in all of the shapes end up being very dense, and those that aren't in all the shapes become very sparse. And so this, to a certain extent, is your uncertainty model for structure. So where you've got dense areas, that's the areas that would give you confidence, but you couldn't use that to extract the actual structure from it because you've lost the lines that join those 2 points together. And it's very likely that there would be artifacts as well. Even though I sort of mentioned the fact that solid lines indicate certainty, that didn't mean that I'm a big fan of blurring. The challenge with blurring is that it's messy and it's difficult to see. And I think that it's much better to guide the client through a narrative that shows you the different structural models that you're considering. And like I said, you need to break down your 1,000 possible structural models into a number of classes with variabilities around those classes, and then present those as your narrative and say, well, we've got these 5 or 10 different model categories, and there's small structural variations around those. But that's an understandable story that you could present to somebody, even if they're non-technical, because what you're trying to do when it comes to visualization is you're not trying to show your data, you're trying to tell a story, you're trying to present information to them so that they can make a decision based upon that. Now, they can't make a decision if they don't understand what you're telling them. And it's complicated, so you've got to talk them through it. So in my experience, it's a combination of organized visualization plus a narrative. The transparency and the blurring line things are things that have been tried but don't really work. Dotted lines actually do work quite well, work better than blurred lines, and we're used to seeing dotted lines on 2D maps, and so maybe that's the reason why it does work.
Yeah, as graphics.
Yeah,
arts,
me too, please.
Yeah, and in painting, so the highlights are cold, yeah, and the shadows are warm. Okay, that's the rule. That gives the volume to the object. In drawing by pencil, the most dark part is on the border of light and dark. So the shadow is always less dark than the border of shadow and dark. And of course, the most important is the glare. Yeah, the last point that gives the volume to object is a glare. Bleak. And of course, so how to select projection when our road parts, yeah, for engineering, there are several projections on one paper, yeah. So we take A1 or A0 format, yeah, place there several projections and explanations. So that's at first it's a document. So you send a file, someone can change this file, then and else and else and else. If this is a print version of project with specification, it's a document, and it will be other perception, not virtual. So you see the work that is done. To that book, we can slices, add geological slices, yeah, add input data, localities, and those and those. So it could be perceived, I think, more, and one version more более художественная, more artistic version, yeah, for
So from the discussion, I wonder if at the end an image as itself is enough. You were talking, Stefan, about narrative. Maybe we need to accompany the image with some comments or a way to read it or something like that, because the image itself alone is a source of misunderstanding.
Yeah, and I think that you do need a narrative for these images, and for your model. I mean, what happens to the model when it leaves you in terms of communication? So, do you just put a picture in a report, or do you have words with it that explains it? You have to have words with it. You have to tell a story. When it comes to data visualization, journalists are actually very good at data visualization. the New York Times employs about 200 data scientists to do visualization. So they know how to tell a story with data. And the whole process of data visualization is telling the story about the data in a way that's honest. And if you leave parts of the story, then you're going to get misinterpreted.
Yeah. Jan, please.
Yeah, but this information should be presented in a way that it could be understood without explanations, with a flow of time. After 10 years, for example, in an archive. So other geologists, will look at these models, printed models, and he understands the plot, what's it about.
Yeah, I think Jan want to say something. Please, Jan.
Yeah, just if I may add,
Yeah.
from the experience I just described in the presentation, I don't think the visualization itself is the only way how to pronounce the uncertainty. It must be really the active working with the models. I was very surprised how the engineers who were working with the model, they had maybe one semester of geology somewhere 20 years ago at high school, and they really did not understand very well what's going on there. But they were really actively playing with the visualization either by lithology, weathering, or the uncertainty values to show only some parts of the model. Yeah, and this allowed them to actually percept what is more reliable and what is less reliable. Because by the blurring or the change of size of voxels, it's always distortion, which would maybe make me a bit unhappy when I would be dealing with this. And this active work, which means that there must be some software which allows it. Yeah, it may be a bit problem, of course. Then can help the user to really understand what is reasonable and what not in the model.
You mean stencils for every layer? So to extract layer of weathering crust, but with с привязкой, how it will be, but every layer should be connected to the 0 point, of course, that is present on every image.
I meant rather a principle that everything not should be put just into a visualization, like in a blurring or changing size or whatever, but part of the presentation of the uncertainty should be in some active elements in the software which shows the model. Yeah, it means there must be ability to the user to really filter or change the visualization according to his subjective or personal needs. And not only to make it like some final scene that you can play with, but not really change the visibilities and so on actively. I think it's combined.
There are some examples in the chat. There are some examples of blurring, of transparencies, of the size of the voxel changing from place to place. It's kind of noise addition as well on maps. There are several illustrations for that about that in the chat.
So for example,
Dmitro, please.
So in 3D models, there is a light source. There are RGB channels. Yeah, of course. So there could be some problems for the when you are rendering. Yeah, this model. Yeah, that is turning. For example, it's a video. It's easier than show interactive object that can be turned as he wants. So here could be problems because before rendering, it's not a full information.
Maybe we can ask Santiago if he agrees. After your experience and what we have seen today and what you did when it happened, if you would have to publish again a new time, nothing happened so far, and this is the first time you published this map. What would you do differently, in fact? We talked about narrative. Is it a matter of describing better the map, or what do you think?
Well, I think first, Stephen Tyson recommended some warnings, because the problem is that the people doesn't read, scan. I mean, they go very quick. For instance, the origin of the misunderstanding was an article in the economic press, and the people only pay attention to the map. But okay, and they don't see. We are talking about citizens, general public, and the problem behind is there is a huge lack of knowledge of what those data means. That is the problem. So maybe some warnings, maybe, but the problem is that today the social media change a lot and forget the sources. One of the first things that the anti-fake made is, this is the real map, and they refer to the BRGM map. The original map is not that published by the economic press. This is the original map, but you need to put a short explanation of this map means this and this and this and this and this. So maybe some warnings, some will be useful on the map, on the original map. We cannot control. That is one lesson we learned. We cannot control how the discussion about our data, published data, goes in social media. We only can't respond to that line, timeline. I mean.
Yeah, it's more or less the same. We cannot really control how the thing we are showing are interpreted, or sometimes misinterpreted. Yeah. Yeah.
And for instance, the best clarification is, this is an occurrence. This cannot come in the majority of the points cannot be a mine.
Yeah, of course. Yeah.
It's obvious for us, but the problem is for the majority of the people, it's not so obvious.
So still speaking about ways to display, in a way, we have seen that displaying is not enough. We need a narrative, and the narrative has to be dedicated to the kind of stakeholder as well, because depending on the people you are talking and showing result, the narrative has to be different, I presume, as well. Steve, I think you will agree on that, or not?
Yeah. Look, I mean, the whole sort of Spanish fire and mine thing was a real outlier when it comes to misrepresentation. It is a warning, because these things can happen. Social media, as we know, can just take the ball and run in a completely different direction. And I don't think that the guys who created those maps could have done anything better or differently. Having a narrative, having some warning labels on there may have helped, but you can't help bad actors from twisting the truth to their own ends. So I don't think that I would have done anything differently. They did the right thing, getting the professionals in, because professional corporate communications guys, the people who know how to use social media, the people who know how to handle comms crises, are much better than we are at this. But when it comes to the creation of maps, I still think that it's worth somehow including in your metadata some of your own thoughts about the usability of that map, and not just the date that it was created, and not just who created it, but the things that you could conceivably use it for, the things that you could reasonably expect to make decisions from. Things like that. I'm not saying that we need to do that for all maps, but I think that it's worth having in the back of your mind this concept that people see a map and all of your geological knowledge is not immediately transferred to the viewer, and they can't infer the things that you know from your 20 years experience. And so there's a lot of stuff that you've got to put in there for the layman. I mean, maybe you can create a boilerplate that goes onto all the maps. Nobody's going to read it. The bad actors are going to take it. They're going to take off all the warnings and do what the hell they like with it. But you're covered. And when the real journalists get to the bottom of the story, they'll be able to produce the map and say, look, it's clearly got all of this information on it. But I think the whole visualization process is something that's not simply what's seen in front of your eyes. I think there's an explanation, there's a narrative in there as well, because communication isn't exclusively visual.
Yep. Thank you. Is there some other comments or some other, I don't know, ideas or experience to be shared regarding ways of displaying results, and not only displaying, but how to communicate on the results regarding 3D geomodeling? If not, maybe a last point I would like to talk about Jan Franěk from the Czech Republic Geological Survey. I think you are still with us, Jan. You were the only one to talk about very quickly about the legal issue regarding geomodeling. So I think it's really related, because social media is one side, but there are other important related issues, and the legal issues are among them. Can you maybe please tell us a bit more about how it works, especially in Czech Republic, and then we will ask maybe for other countries?
Well, I'm not expert in law and so on, so it will be very basic view.
Yeah, when you provide a 3D geological model, you need to add warnings and stuff like that because of these legal issues, I think, no?
Yeah, definitely in the contracts for the models, if we know that they are made for some constructions, we always put there some ambiguity of the models directly into the contract. We have a lawyer at CGS, and with which we created some paragraph in Czech language, which tells in some nice way that no one should believe our model and so on, if I just a bit over-exaggerate. And also to any final report, to every model we have some quite extensive final report, which says where are the data coming from, how they were used and processed, how the model was built, and also what are the ambiguities and so on. And it should be used with care. Yeah? There is always several pages written on uncertainties of the model, then. I'm sorry, just the last point. And as I was showing, so that really no one can say, I didn't know about it. Yeah. So we use these 3 ways of incorporating the uncertainties into the model. It means it's in the voxels, in the volumes, and in the source data. So that I think we have covered what is expected to be or the most risky parts of our jobs. And of course, there are some normatives in Czech Republic which are dealing with engineering geology. Yeah, it's not this geological modeling; it's an edge of engineering geology and let's say scientific geology or structural geology. But there are some normatives which say how the exploration should be done, which are the common or let's say expected stages of exploration and how the results should be treated. It doesn't talk literally about models, but the models can be somehow linked to these individual exploration phases.
Yeah, but I presume that you, with your report, you also deliver the model in, I don't know, in voxel format, something that can be usable by the client as well. Is it the case or not?
Yeah. That's the point. The report is just some supplementary material.
Yeah. Okay. I wonder because the model itself, I mean, the files are dissociated from the report. Of course, you make the link in the report, but if somebody used the files without any of these warnings and so on, is it an issue or? You understand what I mean? Because the report, it's a report, but you can in I don't know, in a few years somebody could use the files themselves without any look at the report and so on.
Yeah, you're right that even if report is given, I have this bad experience that almost no one reads it really.
Yeah,
they just open the page and maybe go through conclusions. That's all.
Yeah.
But for this is just legally covered in a way that for every model we have some letter. How is it called in English? Simply some protocol that we passed the results to the authority which is paying us. Yeah.
Okay.
And that is written. We have supplied the model plus report plus and which formats and so on. So in this, it is well stated what was given out. And so no one can say we did not know about, and the rest is just on the stakeholder or the company who is dealing with it. And of course, it's like it's a specialized outcome. So if someone who is not educated works with it, he can get in trouble definitely. But it's like with everything.
Yeah, it's a very important issue, and I wonder we have the example of the Netherlands as well. I don't know if maybe Jan or Chris are still with us, but the work you do, guys, at the national level in the Netherlands is in the law, in fact. So that means that what you produce is really the reference. In terms of legal issues and dealing with uncertainties and so on, could you tell us a bit more about how it works?
Yes, that is correct. We have this system which is called the key registry of the subsurface, which includes data on the subsurface, but also the models that I showed earlier today. And government bodies are obliged to use both the data and the models when they do something that involves the subsurface. And that also means that they can expect some kind of quality, of course. If they disagree, if they think, well, I've made a borehole of my own or a CPT or whatever, and it is different from what the model predicts to be here, then they can file, well, not a complaint, but they can give feedback to the geological survey, to the producer of the models, and we have to react on that feedback. But we are not liable in a legal way. So we have to explain why we think their observation is different from the prediction or the estimate from our model. But even if our conclusion is we made a mistake, then we are still not liable. But we have to explain why.
Yeah, for sure. So you need to retrieve in a way to trace how the results were produced and so on. Yeah.
So even also older versions of the model always have to be reproducible. Yeah. That is work for us to do. Right? We cannot just produce a model in a project and then keep the results and throw away everything that is intermediate. We have to keep everything because maybe in the future, maybe in 7 or 8 years' time, somebody will ask questions about that model, and then we have to, well, investigate everything, retrace where it went wrong. Yeah.
Okay, thank you for this explanation. It's very interesting, and so I think it's time now to conclude. our workshop. So it has been a pleasure to share these 2 days with you. A lot has been shared about uncertainties. We have seen about concept sources, communication, applications. We have discussed about case studies and the ways uncertainties are handled in some geological surveys using different methods and tools. I remind you that the sessions were recorded and the replay will be soon available on the GSEU project YouTube channel. We were quite a lot of us during these 2 days, depending on the session, but between 70 and 120 and even a bit more. So it's interesting that the participants were a mix of geologists and geomodelers, but also geostatisticians, and both on the user side and on the, I would say, on the developer solution side. Maybe there was a lack of people, maybe of stakeholders themselves first, and maybe people who could help in communication. We have some presentation on that, but maybe this is something we need to keep in mind and to ask themselves if we are the best to tell stories and to have the narrative we were talking about. I think this is really important. So a lot has been discussed. For instance, we have seen that the main source of uncertainties comes from data and from interpretation. There is a quite good confidence for the modeling methods themselves. This is what we have seen yesterday, especially during the pool and the Menti. But if I would just bring 3 points when leaving the workshop, I think for me, it would be the fact that methods for quantifying uncertainties exist, but there is a lack of operational tools to really being able to apply them. The next point is that in geological surveys, most of the time we do 3D geomodels for application, not just for doing 3D geomodels, of course. So we certainly need to adapt the amount of work to spend regarding the computation of uncertainties. We need to adapt it to the real request of the application. And maybe the last point is about learning from other fields such as weather forecasting. We discussed about that, especially regarding communication, but it is aligned with the narrative aspect of communication, I think, and the way they can communicate on results and probabilities or uncertainties. So to conclude, I want to thank all the presenters for their very informative and high quality presentations. And also Chiara Damborghi and from the Italian Geological Survey, and Eva Sinkaruk from the Polish Geological Survey for animating the session yesterday and this morning. The workshop was prepared by the 3D geomodeling core team of the GSEU project, with a special thanks to my colleague Simon Lopez. And I don't forget Daniel Marco and Renata Barros from our surveys, who helped a lot in the preparation of the workshop and for running the interludes and the Menti with Daniel. And the final thank you, of course, goes to all of you who have participated in these 2 days of discussion. I hope that now uncertainties are less a myth, and you can see at least some concrete possibilities for quantifying and communicating these uncertainties. So please stay tuned for the next GSEU workshop about 3D geomodeling. There will be certainly another one on the second half of this year, and enjoy the rest of your day. Thank you, and bye-bye.